Doesn't take superhuman strength to bend light. All you need is plastic, water, and optical fiber. Here to explain all of this is the wise guy, Matt Sullen. How does this work?
Well, you think of light taking the straightest or the quickest distance between two places, and it usually does. Well, it always does, actually. Now, if you just shine a light from one place to another, it just goes in a straight line. But suppose I want to shine it through some air and then through some plastic from one place to another. Let's see what happens. Let's say I want to shine the light at my finger down here, and I'm going to do it from up here with the laser beam. Notice that it misses. Even though the laser is pointing at my finger, what I have to do is I have to hit out here a little farther in order for it to hit my hand. So it actually goes this way, then it bends, and then it goes into the plastic. The reason for that is that light travels slower in plastic than it does in air. And it wants to take the quickest route between up here and where my fingers are, and the quickest route is to go a little farther in the air because it goes faster there. It's like going on the highway. And then it gets into the plastic where it goes a bit slower. And so it turns out, for that sort of argument, for that reason, that you always get light bends sort of towards normal incidence as it goes into a denser medium. This thing has a higher index of refraction. And that's very...
The huge piece of plastic, would it continue to bend in a circle?
No, it only bends once. So it only bends at the interface between the air and the plastic. So the interesting thing is I can almost have this thing going in a grazing angle, coming in at a very shallow angle, and it still bends in. That means if I kind of play that backwards, if I shine light from the inside, what can happen is I can find an angle for which it doesn't get out anymore. Okay? And so this is called total internal reflection. So you can see right now that the light just bounces off the surface and it doesn't get out at all. It would mean that I would have to shine somehow at an angle below the surface, which is impossible if I was shining light back into it. So this is total internal reflection, and this is how optical fibers work. If I hold this thing from its side like this, maybe you could see, and now if I shine the laser like this, you can see it bouncing around in there, and it's stuck. It's trapped inside. And so the light just can't get out. It's stuck in the plastic. And so it can go a very, very long distance this way.
So if we were in a completely dark room, you would not see light bouncing out of there. You wouldn't see the end to that laser.
It basically, well, you can see the spot on the wall over there. It just bounces around inside, then it comes out and it hits over there. Now the reason you can see that green at all is that this piece of plastic is kind of crappy. And so some of the light gets bounced out. If this was a really good piece of plastic, you would see nothing.
Only the finest plastic on the show.
Sure.
It's just crappy enough. It's a beautiful, crappy piece of plastic. And this is how fiber optics work. So if you hold the end of this thing and point it toward the camera, and I'll just shine the laser in this end, you can see that the end of it gets green over there. It sort of flashes green
there
every now and then.
Sure.
Okay. And so what happens is this is how optical communications work. This is how your phone company sends voices from one place to another. They modulate the laser beam, which then travels along an optical fiber, and then you pick it up at the other end.
So these bending light waves, that explains why if you're trying to pick up an object that's, say, in the bottom of a pool, it's very hard to grab.
Right. If you stick your hand into the pool, it looks like it's kind of bent outward.
Right.
And that's just an optical illusion because light gets bent as it enters and leaves the water. It's not really true. And you can do this experiment at home, actually. Here's a glass of water that I just put a little coffee creamer in, so it's just a little like the crappy plastic, so that the light will bounce off it. And so you can actually see the nice laser beam in there. And if you look from the top, you can actually see it bouncing around inside, and so on. So it's very cool.
And these are not very technical lasers that only wise guys have.
Well, no. You can. This one I think I got at the gas station for $6. And the green one is still a little more expensive, so that one I had to borrow from the university.
Be careful with that. I need that back.
Oh, there we go. You can have it. It's a lightsaber. And anyways, so but these you can get cheap, and these you'll be able to get cheap in a few years. But the color doesn't matter. You can do this thing with the red one too. It's just harder to see because it's not quite as bright.
Sure.
Okay. Now, next week on Wednesday is the 2nd of July. Okay, Independence Day, actually. So we're going to, in honor of that, do some kind of explosion or rocket or something. I haven't figured out what yet. I'm going to get somebody in the chemistry department to help me, I hope.
So looking forward to that.
Looking forward to exploding
things. The wise guy, thanks for the lesson on light, and thanks for the lightsaber. Let's take a look at our Champagne Sky Cam. Kind of hazy this morning.